Great. So thanks for tuning in to our STOC talk on outcome indistinguishability. I'm Michael Kim, and this is joint work with Cynthia Dwork, Omer Reingold, Guy Rothblum, and Gal Yona. In this work, we revisit the underlying goals of individual risk prediction. So typically, the goals of risk prediction are framed as finding some best fit hypothesis. For instance, the agnostic pack model formalizes this goal by first fixing a hypothesis class, then learning a hypothesis H that achieves loss, in this case, the squared loss, that competes with the best hypothesis in the class. While this framework has been very wildly successful in formalizing the goals of learning and machine learning, and for learning accurate predictors in diverse domains, a critical downside of the PAC framework is that it only considers overall performance, right? And it doesn't make any requirement on where the errors should or need to occur, which can lead to downstream unfairness, for instance, errors concentrating on a specific subpopulation. So here, if we try to impose some sort of fairness, it necessarily is a constraint and therefore must be traded off with accuracy. So in our work, we're going to propose a new paradigm for learning, which we call outcome indistinguishability, that frames the goal of learning not as finding a best fit hypothesis, but instead as finding some model that in a sense is indistinguishable from the true outcome model, which we'll call nature. So to understand this goal at a high level, consider the following challenge. On the left, we're going to take an individual and an outcome sample from one of two models, either from nature, from the true individual outcome pair, or from our model of nature. Then we'll pass this sample to a distinguisher. And the distinguisher's job will be to guess whether the individual outcome pair came from nature or came from our model of nature. And our goal will be to develop a model where the distinguisher can't succeed much better than random guessing. More formally, we'll assume that nature is a joint distribution over individual outcome pairs, but we're not going to make any further assumptions. Nature could operate arbitrarily. For the model of nature, we're going to assume that we're working with a predictor, p tilde. So a predictor, p tilde, is just a mapping from individuals in this domain X to in the interval 0, 1. And we note that any predictor induces a generative model for outcomes. Specifically, given an individual, we're going to, that will sample from nature, we're then going to resample their outcome according to the Bernoulli distribution with parameter according to their prediction, p tilde of X. So we have two distributions, this one that nature that I'll denote dnat star, and then our model of nature, which is dp tilde, parameterized by a given predictor. So then with this notation in place, we can restate our goal, which is to learn a predictor, p tilde, whose model distribution, dp tilde, is indistinguishable from nature's distribution. And the question we have to ask ourselves then is indistinguishable to whom? So for instance, if we allow any distinguisher, then it's not hard to see that the model distribution, dp tilde, would need to be statistically close to nature's distribution, which from a small sample is impossible. Thus, to have any hope of achieving this goal, even statistically, we're going to need to consider a computational relaxation. Which leads us to the formal definition of the OI framework. So first, we're going to fix a class of a bounded class of distinguisher algorithms, which we'll denote A in this talk. And these algorithms will take in individual outcome prediction triples and map them to 0, 1. So there'll be some class of Boolean functions. And then we say that a predictor is A epsilon OI, A epsilon outcome indistinguishable, if for all algorithms in the class, for all A and A, the probability that the distinguisher returns 1 on samples from nature and samples from the model are within epsilon of one another. So note that in both cases, we only allow the distinguisher to look at the prediction according to p tilde. You'll note that p tilde is an input on both sides. And this is important. In particular, the distinguisher's only access to nature is through the outcomes. So you'll see that they see either y star from nature or y tilde from the model. And this is where the name outcome indistinguishability actually comes from, the fact that the distinguishers are only seeing an outcome. And in the paper, we explore variants of the OI definition, studying their various properties as learning desiderata. So before going into the details, I want to speak about a pretty direct analogy between outcome indistinguishability and the classic notion of computational indistinguishability. So computational indistinguishability is widely used in cryptography and pseudorandomness and complexity. And here, a prominent perspective is that randomness is in the eye of the beholder. And so in OI, we're suggesting that perhaps individual probabilities are in the eye of the beholder. That when your goal is prediction, it really depends on what your tasks are downstream and who is going to be using these predictions. And so hopefully the predictions you come up with are indistinguishable to whomever is going to be using the predictions. And so our framework puts forth this idea that maybe it is possible to learn simple generative models that look like nature for all intents and purposes. So good. So earlier I presented a specific definition of OI. In fact, in the paper, one of our main contributions is not just defining a single notion, but a hierarchy of notions of various different variants of OI based on the access that the distinguishers get to the prediction model itself. So in the first level, no access OI, the predictors only receive individual outcome pairs. They don't get to see the prediction at all. Then in the next level, sample access OI, the prediction, they also get to see the prediction. And this is the version that I presented on the earlier slide and the main focus of this talk. And then the next level, which we'll also discuss, is oracle access OI, where instead of just getting the fixed prediction, p tilde, on the sampled individual X, the distinguisher can ask queries about arbitrary individuals after seeing the individual that has been sampled and that they need to make a binary decision about. Good. And again, I emphasize that the only access to nature is through outcomes. And so in the paper, we explore a few other variants that aren't on this slide and discuss their various properties and argue formally why this outcome indistinguishability makes sense over some of these other variants you might consider. Good. So our first main result actually shows a strong connection between OI and the so-called evidence-based fairness framework, also called multi-calibration. So this framework comes from a growing literature on algorithmic fairness. It takes the perspective that the first thing that you should do with a predictor is try to learn a predictor that understands the evidence at hand and to reflect it as well as possible using the statistical and computational resources available. And to do this, not just on the population overall, but even on subpopulations. So for instance, the main notion, multi-calibration, aims to ensure well-calibrated predictions across all computationally identifiable subpopulations. So perhaps you want to pause the video and look at these definitions. The idea is that we're going to require a prediction to match the expectations over various subpopulations, which we can think of as being defined by a computational class. And multi-calibration takes us a step further using a notion called calibration that is common in the forecasting literature, less common in the computational learning theory literature, but of note and actually considerably stronger than this accuracy or unbiasedness notion. Good. So the main question you should ask then is whether we can even achieve this notion. Maybe it's all well and good if it's a nice definition, but we might not be able to achieve it. So pushing this connection further, our results demonstrate, based on the tight connection between OI and multi-calibration, that we can achieve this notion. So specifically, we have a certain computational equivalence between OI and multi-accuracy and the stronger variant of OI and multi-calibration. So what does this say? It basically, the result says that for any collection of subpopulations C, we can turn it into a class of distinguisher algorithms such that A sample access OI implies C multi-calibration, and in the other direction. We lose a tiny bit in the accuracy parameter, but in a non-material way. Good. So just off the shelf then, by appealing to prior work, we can say that OI is feasible and in a bounded sample complexity, and arguing that we can actually implement these predictors in a complexity that scales with the class of the distinguishers. Good. So that only shows a positive result for these first two levels. In fact, in the paper, we generalized the result from the learning algorithm given for multi-calibration, showing how to learn OI predictors directly for all of the variants we consider. So the theorem is constructive and works by giving a boosting style algorithm that looks for sets on which you can distinguish the predictor from nature, and then updating when you find such a distinguisher. And so, as I mentioned, the algorithm is statistically efficient, and it's oracle efficient in the sense that it can be implemented computationally efficiently if you can solve a certain agnostic learning problem. So I'll emphasize that, again, that the construction holds for any choice of nature, even arbitrarily complex natures. And we still are able to upper bound the complexity necessary to generate these indistinguishable outcomes. However, one thing that you've probably noticed is that the top two levels, this no access and sample access, both have efficient constructions, in the sense that the complexity scales linearly in the time of the distinguishers and polynomially in 1 over epsilon, the accuracy parameter, whereas this oracle access OI scales exponentially in the accuracy parameter. And so then we're not happy with this. A natural question to ask is whether this inefficiency is just because we're being lazy and didn't find the best construction, or if there's something inherent. And so in fact, we show that the inefficiency for oracle access OI is inherent in a sense. So this is our second main result, that there exists a nature and a collection of oracle access distinguishers that run in time t, they're efficient, such that any predictor that satisfies a oracle access OI, or a epsilon oracle access OI, requires time t to the 1 over epsilon. So some exponential dependence in 1 over epsilon is necessary under a certain weak variant of the K-clique conjecture. So specifically, I write it down below. The connection to K-clique and to sharp K-clique comes from is quite generic. One could imagine basing it on a number of hardness results or conjectures. We do this in the paper. And I think the main way to think about it is that actually just at the level of generality that we're working for Oracle Access OI, if you were to significantly improve on the construction, it would imply a breakthrough in various complexity results. So at a very high level, why does sharp K-clique show up in this presentation about indistinguishability in predictors? So the lower bound comes from constructing a nature and a class of Oracle Access distinguishers such that computing the outcome of an individual according to nature is based on a hard problem. So in particular, it's based on the number of K-cliques in a certain distribution of graphs. So the individuals will correspond to a graph. But the distinguishers will be very efficient, but by using Oracle Access queries, can run a sort of random self-reduction. And so any AOI model, any model that satisfies Oracle Access OI, it turns out must actually compute this hard problem correctly. So collectively, this intuition argues that achieving this AOI must actually be computationally intensive, and we formalize this in the paper. But basically, the reason that sharp K-clique shows up is because there is a known worst case to average case reduction and various properties of that make it a distributionally hard problem. Good. So the main takeaway here is that Oracle Access is actually a very powerful property in distinguishers. If you allow the distinguishers to query the predictive model in question, to query P tilde, they can do things that they couldn't do if they only had passive access in the same amount of time. So good. Intuitively, part of the reason that this happens is that the distinguishers can check for correlations across the outcomes of various individuals. And knowing that your predictor is good at making predictions on some class of individuals, it could hope to leverage that to understand what the outcome should be for a new person. So in particular, they can use these local checks to enforce global consistency with nature. So yeah, one more time, I think the way you should interpret this result is as saying that at the level of generality that we're working at this very generic level, not making any assumptions about the nature of the distinguishers or about nature, the construction is essentially optimal. And the real question is whether you can achieve Oracle Access OI more efficiently if you make certain domain-specific assumptions. So I think it's a really good question to ask under what conditions on nature or class of distinguishers, these kinds of things, do efficient Oracle Access OI predictors exist, and what are their properties? Do you still inherit sort of the strong protections that would be afforded by Oracle Access? Good. So I think a practical takeaway of this theoretical result is that in the real world, there's a lot of discussion about auditing algorithms. And what our results seems to suggest is that pretty generically, giving Oracle access to these auditors, allowing them to query the models that they're interrogating, is much more powerful than just looking at historical records. And so I think there's some practical import to this theorem as well. Good. So to recap, we talked about this idea of outcome indistinguishability as a framework for understanding the meaning of individual risk scores and as a new goal for prediction. We defined a hierarchy of notions based on the access that we allowed to the predictive model P tilde. And we saw that oracle access gave qualitatively different results as an indistinguishability notion than a lot of prior notions. And we discuss a number of further aspects and extensions in the paper: multiple samples, lunchtime access, connections to various other literatures as well that I don't have time to discuss today. So I'll just finish by putting forth one discussion point. And that's that OI is really designed, and our goals here were to generalize this work on multi-group fairness, or this evidence-based fairness framework. And really, I think the distinguisher perspective really gives a nice lens to explore these fairness notions in the future. And so in particular, one idea that is tempting to state, but a bit more challenging to formalize, is that the idea that a fair predictor should somehow be indistinguishable from the ideal predictor. Now, if the ideal is nature, if you're confident that the samples you're getting are from sort of the ground truth, best possible distribution, then maybe our framework of OI basically already handles this. But I think a really interesting question is to ask, like, what if the samples you're getting aren't from the ideal distribution? What if there's a different ideal predictor out there that you can imagine, but you don't have samples from? Can we use this indistinguishability framework to still formalize the goal and the task and make progress towards that goal? So I think really our main contribution, overarching everything, is setting up this framework. I think it's already shown to be pretty fruitful in different application domains. And I think there's many possible extensions, and I hope some of you will help us work on them. So thanks so much for coming by and listening.